This talk is the introduction of Amazon SageMaker Debugger. If you don't care about that, then you're in the wrong place. But if you are, well, welcome. My name is Andrea Olgiati. I'm a senior principal engineer with the SageMaker team here at AWS. And we have our guest, Alexander Carlson, from our friends at Autodesk. And he's going to give us his experience working on SageMaker Debugger. So today we're going to talk about Amazon SageMaker. For those of you who are not yet familiar with it, we're going to talk about the challenges that practitioners face when training ML models. We're going to introduce the debugger, and we are going to show you some sample notebooks and how you can use this debugger in your own projects. And then I'll hand over to Alexander, who is going to tell us about his real experience with SageMaker Debugger. Okay, so let's start with why we're here, what we're doing, what SageMaker is about. At AWS, we want to put machine learning in the hands of every developer. There's a lot of barriers when it comes to introducing ML techniques in your applications. There's a lot of learning that has to be done. There's a lot of specific technologies and terminology that are at times inaccessible to your average developer. There's a lot of knowledge that one has to have before they become proficient with machine learning. Our mission at AWS and with the SageMaker team is to lower that and make machine learning accessible to your everyday developer. The analogy that I think of is databases. Most developers know how to use databases today. We want to make machine learning as accessible to the average developer as databases are today. SageMaker is a platform that allows developers and builders to build, train, and deploy machine learning models quickly and at scale. It's composed of a whole bunch of projects. You can see them from the left to the right, from collecting ground truth for machine learning models, to a marketplace, to algorithms, to notebooks. And today we announced a new feature, the Quick Start notebooks, that allow you to significantly improve your time to coding. It allows you to train and tune models. It has built-in support for reinforcement learning. It has support, new as of today, for experiments, debugging. It has an autopilot mode that allows you to bring data and obtain an optimized model that you can then customize without having to understand really a lot of the details underneath. It can deploy models on the edge with Neo, and it also allows you to deploy models on AWS instances with one click, one command. You can take a trained model, deploy onto AWS instances. And on those instances, as of today, you can turn on monitoring. Monitoring allows you to detect whether the distribution of data that you trained on is still the same or it has changed. All of this is under now, as of today, the umbrella of the Amazon SageMaker Studio IDE, which is a dedicated, brand new web-based IDE for machine learning. Today, we're going to focus on one of these components, the debugger. It's a tool that allows developers to really understand how the process of training a machine learning model works, and will demystify a lot of the mystery around it. And it really brings to the developer the ability to inspect data, the data that is used whilst training a machine learning model. So Amazon SageMaker, again, to focus on the training part, and we're going to focus on the debugger in a second. Amazon SageMaker allows customers to train machine learning models in essentially three ways, right? And on the left, we have algorithms that were written, designed, and implemented by us. These algorithms were chosen for their applicability, for their simplicity, for their scalability. We built algorithms that scale with your data set, with the number of instances that you provide. You don't have to worry about that. We have taken care of all that. Popular ones include XGBoost, matrix vectorization. You can read the list. Those algorithms are built so that we do all the work. You bring your data, you set some parameters, and you go. For those who want a little bit more control or maybe are interested in deep learning, in the middle we have support for the most popular deep learning frameworks in the world: TensorFlow, Keras, MXNet, PyTorch, Gluon, and you can use them under the support of Horovod. Horovod is a very popular library for synchronizing multiple workers. You can scale up training. Yesterday, Peter DeSantis described some of the results that our team has obtained with scale-up. We've been able to train BERT and Mascar CNN, very popular algorithms for NLP and image segmentation with really high scalability. On the right-hand side, if you really want to bring your own recipes, you can bring your own container, and SageMaker will run your container as is. You have absolute control. You can bring in the ingredients that we provide for you, and you can package them up, put it in ECR, and then start a training session. SageMaker is fully managed, distributed, auto-scaled, secured. Everything that we do revolves around those principles. Even so, even if you do the thing, if you use the best practices, even if you use the algorithms that we provide for you, training a model has some aura of magic box around it. You bring your data, you hope to train a model, and then it doesn't work. Have you ever been in that situation where you bring your data, you try and train, and it just doesn't work, and you stare at graphs on a screen and try and understand what's going on? Well, let's take a step back. This process happens because we have often large neural networks with many layers. Like, this is a complex architecture that you're trying to optimize, whose weights you're trying to optimize for your task. It has many connections, it's computationally intensive, and it's really hard to inspect, debug, and profile what's going on. It's a black box in many cases. So some time ago, we said, okay, what can we do to make this process of debugging accessible? We started from what customers have available today. Today, the state of the art is to insert print statements in your code. I don't know if you've ever done it, but today you can print values of intermediate layers. You have to go into the architecture of your model and type, insert a particular node, or add a magic statement. You have to analyze the debugging data manually. You can load them up in something like TensorBoard and try and understand what's going on. You can use tools for charting and make this process work for maybe 1, 2 instances. But if you're trying to do this repeatedly and you have to look at graphs to understand why your training isn't working, this process isn't scalable, right? We deal routinely with customers that have maybe trained 1 model and customers that train hundreds, thousands of models. And we thought, okay, can we build a system that scales with these customers? And yes, we believe we found a better way to do that. And that way is SageMaker Debugger. SageMaker Debugger is a tool for the analysis, debugging, and alert generation on data coming from ML model training. The debugger gives you complete visibility into your training process. It allows you to inspect the debug data visually and also programmatically by presenting it to you with through a NumPy interface, which is very familiar to the data scientists in the room. SageMaker Debugger allows you to automatically capture the data. you don't have to specify what data you want to capture in your source code. This is one of the fundamental changes that we made. Whilst maintaining your compatibility with a whole bunch of tools, we allow you to say, capture this collection of tensors, of gradients, of scalars. We package them up for you so that you can say, hey, capture all the gradients, capture all the weights, and save them at particular intervals so that you can see how your training is progressing over time. We do SageMaker Debugger does automatic error detection. As part of the SageMaker infrastructure, you can start a training job and also say, tell me when this event happens. If you're familiar with assert statements in your source code, it's similar concept. You say, I want you, SageMaker, to tell me when this condition is met and alert me. And based on that alert, which can be captured as CloudWatch events, I can take actions. I can page somebody. I can send an email to somebody. I can stop training because this particular training job is going nowhere. It works for single machines and across distributed clusters. It works across distributed runs. It allows you to take this data that you captured today and look at it over time. And it's integrated with Amazon SageMaker Studio. How does it work? As you train your model today, like you normally do, you can ask SageMaker to send data to your own bucket. We don't look at the data. We have no ability to look at your proprietary data. You send it to your bucket. It's encrypted just like other data within SageMaker. And we, as part of the training job, you can spin up rules. We call rules essentially these assert statements. They are ways for you to say, tell me when this condition happens. We have first-party rules that we have written for you if you wish to use them, but we also give you the ability to write your own rules. And essentially a rule is a piece of code, Python code that uses NumPy, just like you normally would, and it says, hey, look at the output of the 7th layer of this network and tell me when this condition happens on the output. All you got to do is just write some NumPy code. When these rules trigger, when these alerts fire, you can trigger CloudWatch events, stop the training. You can pull up a notebook and just look at the data. And we provide a full SDK for you to look at this data and analyze it as you slice and dice it as you wish. Compare with previous runs. And we also provide built-in visualization using SageMaker Studio. We're going to give you some screenshots of what this tool can do for you. This is a view of the SageMaker Studio IDE. Again, this IDE was announced today. And it provides built-in support for SageMaker. This is a very simple rule that I think looks at the output of the system and measured as loss. And it also has, let me rewind. It has two built-in rules. One rule that says, tell me when the loss is not decreasing, which sometimes happens after you train for a while. You're no longer making progress on your training, as measured by the loss. You can also check, in this case, whether your weights have been initialized correctly. We spent a lot of time with our data scientists to establish best practices for weight initialization, for instance, or for weight updates, the ratio between updates and gradients. We have worked with our internal team to say, hey, what are the things that practitioners should be doing? Can we cast those into guidance that we can give our customers? And so we built a whole bunch of rules. Two of those are written there. The third one is a custom rule that you can write. You can provide a piece of Python code, bring it to us, just write a little bit of of code as you invoke training, and that rule will be invoked for you. Now, the interesting thing here is that these rules are implemented simply as new parameters to the training job call, or to the estimator interface. I'm going to say this in a different way. The code above the line that says new parameters is what you had before. And the code below is all you have to do to turn the debugger on. You no longer have to go inside your neural network architecture and just type in magic commands to emit data. All you have to do is just invoke those rules. We take care for our first-party rules of capturing the right data. But if you want to capture your own data for your analysis, you can absolutely do so. Data that gets emitted is captured and is visualized for you as part of the chart on the right. And we will be adding more charts as time goes on. And you also have the ability to see on the right-hand side, on the top part of the picture, the progress of these rules. Essentially, you can say, hey, has this rule fired? Has this assert condition happened yet? And keep a real-time view over each training job. These rules are, again, we have a collection. It's visible in documentation. You can peruse it as you wish. But these rules really allow everyday developers to take the wisdom of the expert practitioners and apply to their training job. Once a condition fires, you can get alerts. You can, again, steal from the SageMaker Studio IDE. You can see, hey, this particular rule fired. As you can see in the top left, it says issues found 23 minutes ago, because I looked 23 minutes ago, something happened. Because of that, I can do two things. I can look at the logs, and I can see the details of the tensors, of the gradients, of the scalars that made this rule fire. I can also issue CloudWatch events. I can look at these data in CloudWatch. I can do the normal things that I can do with my CloudWatch logs. I can send it somewhere. I can alert it. I can grab it. I can put it into groups. And also, on the bottom left, I can also observe the location into which the data that was produced by my training job, the internal traces were deposited. They are in my own S3 bucket, and I can refer to them using an SDK, and we're going to look at that in a minute. Here's another example. When I run multiple training jobs, maybe as part of an experiment that I'm constructing, I want to compare the loss between multiple experiments. I want to look at how one trial, I should say, compares against the other. Loss is usually a good indicator of how that works. We capture loss, we save it for you, we send it to the right place, we show it automatically for you in one of the panes in the Studio IDE. You don't have to add any statements to your training job. You will notice that on the left-hand side, we have the ability to operate on training jobs, call them by name, call rules upon them, and just identify the data that they create and index it in so as to give me the ability to compare runs, to compare losses, to compare the triggering of rules. I can do this in Studio, or I can just fire a Jupyter notebook or my favorite Python editor. I can run a script through our SDK. I can obtain this data, and I obtain it as a NumPy array, and I can do things like plotting the average of these gradients. If you look at the top right corner, I take a tensor, which is the output of a layer in this case, or a gradient in this case actually, and I say, hey, for every step where you save the data, take the tensor, the multidimensional representation of the gradient, take the mean, and just print it. This is something that is much simpler to deal with for your everyday developer than thinking about gradients. These are just matrices that you can just plot and compare and slice and dice as you wish. SageMaker Debugger has been instrumental in us getting better insight into how we create, how we build, how we develop a lot of our own internal neural networks. And we've been working on this for quite some time. And as part of the development, we asked some of our trusted partners to help us by trying this out. And one of the partners that we asked for is Autodesk. My friend Alex is going to come up and tell you the story of how he used SageMaker Debugger to make his life easier. So without further ado, Alex.
Hello. All right, can everyone hear me with the mics? Excellent. Excellent. So I'd like to start with an introduction. My name is Alexander Carlson. I'm a machine learning engineer at Autodesk. I work on manufacturing construction products, particularly Fusion 360 and generative design. So as you may already know, Autodesk's offerings span many industries, and there's a pretty good chance that the plane or car that you rode in to get to this conference was made with the help of Autodesk software. So I'm here to talk a bit about my experience getting to try the SageMaker Debugger early as part of a preview run, and the benefits it brought to our machine learning development and deployment process. So we'll start with a bit of how Autodesk uses AWS. So we use AWS services quite extensively at Autodesk, and that includes SageMaker in a variety of use cases. So in construction products, we use SageMaker for helping identify quality risks. So we analyze job site data, and we identify optimization opportunities by analyzing the project documents. That'd be BIM 360. And our construction models, we mainly use PyTorch, Keras, and MXNet for that. So in manufacturing, SageMaker is used for generative design. The machine learning in generative design is based on TensorFlow, and in the next slides, we'll be diving deeper into that topic. So yeah, we've got a lot of cool stuff going on with SageMaker and Autodesk, but we're going to be primarily focusing on generative design for this session. So what is generative design? So generative design is a feature within Autodesk Fusion 360 that puts engineering excellence in the hands of everyone. So like how AWS is trying to put machine learning in the hands of everyone, we want to put the ability to design a spacecraft grade part in the hands of everyone. It turns the design process for parts on its head. So in traditional manufacturing, you would model a part yourself using CAD techniques with a goal in mind, and then you would test it, hoping but not knowing that it will stand up to the forces that you designed it to withstand. So doing this is neither fast nor optimal, as the best possible shape will probably be something that would take hundreds of hours to model manually. It's going to look very complex and very organic, because humans tend to design parts with simple lines and curves. But there is a better way, and that is what generative design delivers. It's a better way to approach part design. So instead of using CAD modeling techniques, in generative design, you specify your the vital connecting geometry, you specify the forces that your part has to stand up to, you specify the materials you have access to, and the manufacturing methods you have access to, and generative design does the rest. So if you have access to an amazing, titanium printer, then you could create this additive result. But if you don't, then you can still get optimized parts for 5-axis CNC or 3-axis CNC. So here's an example that you may have seen already if you were at the Midnight Madness. So this JPL Lander is actually made with generative design. So Autodesk has been collaborating with NASA's Jet Propulsion Lab on a project to design a lander to search further out in the universe for signs of life on other planets. Now, spacecraft are some of the highest performing and best engineered things that humans have ever designed. But since we didn't really find very much life on Mars, we need to go further out now. So this concept lander is aiming to travel 10 times the distance that Mars is. It's going out to the moons of Jupiter and Saturn. So even at their closest orbit, those moons are about 580 million kilometers away, or 350 million miles away. So I said concept lander, but that is slightly misleading because it's not just a concept. We actually built it. So, needless to say, JPL had to rethink the way things had always been done, and they decided to use generative design. Because generative technology in Fusion 360 is manufacturing aware, JPL could simultaneously explore a wide range of different materials and manufacturing methods, which meant that they could make the best choice for any given part on the lander. The legs of the lander were constrained to qualified materials and manufacturing methods, so they chose to go with a 3-axis milling strategy using aluminum. It made most sense for the external structure to be sand-casted due to the sheer size and complex technology. So this lander it would barely fit on this stage. Well, the internal structure used an additive manufacturing strategy as it needed to be able to support 10 times its own weight. They originally thought it would be significant to achieve 10% mass savings, as any reduction in the mass of the landing structure allowed the lander to travel further. The final design achieved 35% mass savings. Though it's important not to look at this simply as a weight-saving exercise, it allows the design to be more flexible and empowered the engineering team to embed design intent into the problem definition. So that's what you get with generative design. You are starting with what you want to accomplish. So this is where our machine learning project comes in. So even with a simple generative design setup, you can get a huge number of outcomes. So this simple bracket setup produced 48 different outcomes, and the most highly optimized results are the ones displayed here in the Explore user interface, where users can explore the outcomes of their generative design solve. However, you're not even limited to that. You're not just limited to the most optimized solutions. So for each one of those 48 outcomes, you also have every iteration of the design optimization process recorded, which brings the total number of results into the hundreds from this single solve. Many customers will choose one of the intermediate iterations because it'll be easier to manufacture, or they like the aesthetics, or because they get a higher factor of safety that they didn't realize was possible. If you specify a minimum safety factor of 5 and an optimization goal to minimize mass, generative design will continue to optimize until it reaches the lightest possible part with a safety factor of 5 using your chosen material and manufacturing method. So this is verified automatically with multiple simulations at every step. However, you might notice that one of the intermediate iterations is only 15% heavier than the final outcome, but offers a safety factor of 10 instead of a safety factor of 5. So that would have been an entirely different product development and engineering cycle using traditional methods, but generative design does that for you. So within minutes to hours, rather than months to years, you end up with dozens of optimized part options that are ready to be manufactured and hundreds of part options that meet your design criteria. And this is all from one solve. So this is what it might look like if you were to try to look at every outcome of a generative design solve at once. We call this generative overwhelm. Now, when presented with hundreds of outcomes, you can imagine it might become a bit difficult to find the perfect part, the perfect result that you're looking for. So every result produced will be optimized and every result will meet your design requirements. You can pick any one you want. But you want to find the best one to send to the manufacturing floor. One that may not only meet your design requirements, but also capture the imagination of your customers with its aesthetics. So we've developed a solution. It's Project Kepler. It's visual similarity grouping for generative design, powered by machine learning and trained on AWS SageMaker. Kepler enables an option within the generative design explore space to group your results in a way that a human would group them by visual similarity. So as you can see in this example, there are 3 clear groupings between the brackets produced here. We might call these groups minimalist in the dark blue there. You could call them latticed in the light blue, and you could call the one in gold thin beams. So, yep. We participated in a preview of the SageMaker Debugger to see how it could help us with Project Kepler and our other machine learning models with rules for monitoring training jobs and the ability to visualize the internal structure of our model as it's training. So for our parameter sweep using SageMaker Debugger, we were able to kick off 10 training jobs at once instead of the usual 1, which would run sequentially, and then it would eat the time and the compute cost of the jobs that produce suboptimal results. And we were able to do this with no change to our code. So here's an overview of the benefits we experienced, and I'll go into more detail on these on the next slides. There are 2 main things that SageMaker Debugger enables that we found most valuable. Number 1 is training in parallel with SageMaker Debugger rules attached to multiple jobs, massively reducing the calendar time and the compute cost compared to running jobs in sequence and comparing the results of jobs after they've run to completion. So next is the ability to gain deep insight into the internal behavior of our model as it is training by attaching debugger hooks to the training process. This allowed us to visualize the weight distributions, the performance of our gradients, and the layer outputs, and led us to make model changes that ultimately reduced the number of convolutions we were using by 33%, reduced the model size by 42%, and increased the embedding quality produced from our autoencoder. So by attaching rules to the execution of our training jobs, we were able to start many jobs at once and terminate all but the ones showing the most promise. So the loss not decreasing rule that they mentioned allows you to trigger an alert whenever a job stops reaching a lower loss or the decrease in loss is not greater than a given percentage that you specify. So this is all completely configurable, and there are many rules to choose from, such as detection of vanishing gradients, which is helpful for our model, and exploding tensors. And if none of those suit your purpose, you can even write your own rules and have them running alongside your primary training job. So that's where we got a 75% savings in training hours. Instead of running for a day or more, jobs that were not performing well in our parameter sweep were killed within 30 minutes because they tripped the loss not decreasing rule. So aside from the creation of rules that allow us to execute parameter sweeps in parallel without having to worry about the cost of allowing all the jobs to run to completion, SageMaker Debugger also provided unique and powerful tools for the analysis of our model's internal structure. We were not only able to detect that we had vanishing gradients, but we were able to visualize our gradient structure over the course of training, along with the distribution of weights affected by those gradients and the outputs of our layers. This gave us insight that led us to change the convolution type we were using and reduce the number of layers by 33%. And we also changed our loss function to perform better over the course of long training sessions. So ultimately, we were able to train our autoencoder to a higher degree of accuracy with more detail retention and less information loss in less training time than we were previously using. So this increased autoencoder performance allows us to produce better embeddings, which leads to better design grouping in generative design. So, in addition to better overall performance and faster training made possible by the insights we obtained from using the SageMaker Debugger to visualize our model, reduction in convolutions also decreased the overall size of our model from 290 megabytes to 170 megabytes. This makes deployment much easier and reduces the memory of machines required memory of the machines to run the inference. So also, with the model trained on SageMaker, we can very easily launch compilation jobs that target any valid AWS ML endpoint. So I'm very excited for the general release of SageMaker Debugger, and I'd like to thank AWS for including us as part of the demo. I think it's going to make developing and training of machine learning models much, much easier and cut way down on the time spent iterating to a better model. Yep.
Thank you, Alex.
Yes.
Thank you. I want to do that. I want to design those things.
Yeah, you can.
So thank you, Alex. Before we go into our Q&A session, there's a whole bunch of tutorials and sessions that you can attend. If you're interested in SageMaker, there's a list here on the screen. We have a whole bunch of notebooks for you to use that use SageMaker Debugger. You can just go to the SageMaker website. There will be links there that will take you to ready-to-use notebooks that you can use. You can start from Studio and just play around with it and let us know what you think.
Yep.
And with that, we are done with our presentation. We can take some questions if you wish.
Yeah.
And I don't know, do we have a mic or we just shout really loud if you have a question? Any questions? Any takers?
Yeah.
There's a question over there. We don't have a mic, I'll repeat your question.
Yes.
Is SageMaker Studio already available? Because the post from Julian Simon says Ohio QS Institute, but I was not able to find that in SageMaker.
So yes, SageMaker Studio is available, and it's available in certain regions. Ohio is one of those. If you cannot find if you, for whatever reason, cannot launch it, please let's have a conversation later. We'll make sure that you have access to it, or file a ticket.
Okay.
But it is absolutely available. Any more questions?
Yeah, and if anyone has questions about generative design, I can answer those as well. Yeah. You want to make some cool spaceships or something?
Yes, if you want to learn how to build a spaceship, talk to Alex. AWS cannot yet help you with that. Okay, unless there's any more questions, we're going to thank you for your time and enjoy the rest of re:Invent. Thank you.